Thank you, Chairman. Good afternoon, and thank you for having me today. It's a pleasure to be here. Let me start my presentation by introducing myself. I am Sun-Sung An from Korea University. Today, I'd like to present a 1 megasample per sec 10B SAR ADC. In this work, I propose a triple charge sharing technique as a deck switching method for low power operation. Let me first start with a short outline. First of all, I'll begin with an introduction. After that, I will explain the proposed triple charge sharing SAR ADC. I will explain the top architecture followed by concept, operation, and switching energy saving. Next, we will look at the simulation results. And then finally, I will provide a conclusion. In recent years, artificial intelligence has been widely used in various business sectors and industries. To learn the AI system and interact with the real world and machines, more sensors are required. In many cases, these sensor systems use batteries, so low power consumption is very significant for the sensors and ADCs that read the sensor output. Now let's move on the proposed low power triple charge sharing SAR ADC. This is a top architecture of the proposed triple charge sharing SAR ADC. The TCS SAR ADC comprises SAR logic, decks for high and low decisions, deck switches, and a TCS block that supports the deck switching. The TCS block is added for the low power operation of deck switching. As an example of SAR conversion, let's take a look at a case of changing a pair of bottom plate voltage. Here, I focused on saving the TX energy from the changed bottom plate. As a saving method, the charge averaging technique was used in prior works. When two differential bottom plates are shorted, we can take the half voltage without any supplying references. The TX energy is also saved in half. With the proposed triple charge sharing technique, the TX energy can be saved further with a reservoir capacitor. The saving quantity can be changed with the size of the reservoir capacitor. In this design, the bottom plate voltage is charged up to 70% without supply reference, only with the TCS technique. In the reset phase, the energy saving effect is further maximized due to using multiples of capacitors rather than using only the MSP capacitor. 30% of total switching energy is saved when TCS is applied to a reset phase. As the ADC started, the TCS block is initialized, while two terminals of the reservoir capacitor are shorted. Generally, a massive reservoir capacitor needs a long settling time for expected high energy efficiency. In this work, the reservoir capacitance is smaller than an MSP capacitance, so the ADC can operate with the expected energy saving ability just after wake up, turn on, or initializing TCS block. The gathering phase is the first phase of the actual TCS operation. The reservoir capacitor is connected to each bottom plate of CDEC. There are two meanings. First, the reservoir capacitor is charging the bottom plate toward the target voltage. Second, at the same time, the capacitor is gathering negative charge for the final charge sharing of the TCS cycle. These win-win operations are due to the differential relationship between the positive and negative bottom plate. In the keeping phase, the charge from the differential bottom plates are averaged with a short connection between the plates, making half VDD voltage. The charges of the reservoir capacitor are kept for final sharing phase of the TCS cycle. In the final TCS phase, the reservoir capacitor is closely connected to the bottom plate. With the charge sharing, the capacitor charges the bottom plate towards the target voltage one more time. Consequently, the rest of the insufficient charge is supported by reference and ground. Thanks to the TCS operation, the supplying charges were minimized. Unlike the initial phase, the potential difference was formed in the reservoir lower due to the remaining charge after TCS. Although it is not a large amount, the potential difference is a positive direction, which improves the energy efficiency. Capacitor deck is separated into phases, deck low and deck high. If the capacitor decision is high, then deck high would be switched corresponds to the conversion bit. And if the decision bit is low, then the deck low would be switched. The TCS technique is applied to few MS bits in this work. Here are the 4-bit conversion example. After LSB conversion, the reset cycle is performed with the TCS technique. SAR logic uses 0.4 supply. This helps reduce the logic power. However, if the scaled process is used, the proportion of logic power will be lower, even without the low VDD. In this design, SAR logic 0.4 volt swing is converted to the 1 volt using a low power level shifter. The power consumption of the level shifter is less than that of an inverter with a nominal VDD IO swing. TCS can be applied to every deck bit. Like this blue line, the saved switching energy is decreased at lower bits, but as the number of TCS applied bit increases, the SAR logic energy is increased linearly, shown in green line. As the red line, there is a lowest point of the total energy, which is the third MSB. If the ratio of logic energy is total energy lowered, then TCS can be applied to more bits. Let's take a look at the simulation result. On this page, famous switching methods are compared with this work. VCM-based switching has the lowest switching energy, but it must need additional voltage reference. The charge averaging switching and set-down switching cost more switching energy and common mode voltage variation. This work has comparable switching energy that is similar to the VCM-based switching. This TCS technique only costs 1.2% area in total. As shown in this layout, the reservoir capacitor is just 1.2% area of total SAR ADC, and it is 10% of the total capacitor area. This work has better switching efficiency than other switching techniques, except for the VCM-based switching. The left figure shows the spectrum and Nyquist rate input with a sampling rate of omega sample per sec. The simulated SNDR is 56.8 dB and the FOM is 3.6 femtojoule per step. I want to conclude my presentation with the summary. In this work, omega sample per sec 10-bit SAR ADC is implemented with a triple charge sharing technique. Thanks to the TCS technique, switching energy is reduced to 83% compared to the merge and split switching without common mode variation and extra voltage reference. The chip is implemented in 28nm process. The simulation result shows the FOM of 3.6 femtojoule per step at omega sample per sec with 1 volt analog supply and 0.4 volt logic supply. The total area is 0.0332 mm square. The proposed technique only requires 1.2% of the total area. That concludes my presentation today. Thanks for your attention.